So in this video, we'll be looking at the 3 ways that you need to know how you can add a hydroxyl group to an alkene. So these reactions are things that you'll be coming across and need to be very familiar with in organic chemistry, especially when you make your way to synthesis reactions. It's very important that you know the different types of mechanisms, their reagents, and their differences, because you'll be having to, decide what reagents or what reactions you're going to have to undergo in order to come to a final product. And when you're looking at these synthesis questions, most of the times it's not simply going to be just one reaction. You're going to have to go perform a series of reactions in order to make your way to your final desired product. So it's important that you understand and are very well versed in terms of what each of these different reactions are doing. So, without further ado, let's get into these 3 ways that you can add a hydroxyl group. The first mechanism is going to be, or the first reaction here, right, is going to be an acid-catalyzed hydration reaction. So that's acid-catalyzed hydration. The second one is going to be your oxymercuration reduction reaction. So oxymercuration. And the third one, for which I actually haven't made its own video, is going to be hydroboration. And the reason for that is just primarily because the mechanism for hydroboration is a bit more complicated and unnecessary, in the sense that you often are very, very likely are not going to be required to know the mechanism or draw the entire arrow pushing scheme for hydroboration. But if it is something that you think you guys would benefit from, I can make a video for that. So be sure to let me know in the comments. But in any case, these are our 3 mechanisms, or our 3 different reactions that will allow us to add a hydroxyl group to an alkene. Each of these, in the end, is going to be adding a hydroxyl group, but there are going to be certain very important distinctions, right? For our acid-catalyzed hydration reaction, for instance, let's start with that one, actually, and we can go into more detail. So for our acid-catalyzed hydration, something that's very important to keep in mind is that you can undergo carbocation rearrangements. Carbocation rearrangements are going to be possible in acid-catalyzed hydration reactions. So these are going to include things like your hydride shifts, as well as your methyl or alkyl shifts. So we can have hydride shifts and methyl shifts, right? These types of carbocation rearrangements, they're going to be possible when performing acid-catalyzed hydration reactions. So it's important that if you are okay with that occurring, then you can use your acid-catalyzed hydration, right? As an example, very quickly, if you were starting with, say, this alkene right here, right, this alkene, and we were undergoing an acid-catalyzed hydration, what we would see forming as, first your carbocation, or actually before we get into the actual mechanism, let's just look at the final product, right? What we would see as the product for this reaction would be something that looks like this. Right? We can see a hydroxyl group has been attached to a carbon that is not even involved in this double bond. And that is an indicator that we've undergone a carbocation intermediate. So why is a rearrangement occurring? Well, if we look at the intermediate that forms initially, we can see that we form a intermediate that has a secondary carbocation. But if we can remember, whenever we're undergoing any sort of rearrangement, any sort of reaction, we should always, especially when we're forming a carbocation, be aware of the adjacent carbons. The carbon to the right of the secondary carbon is primary, and the one to the left is tertiary. So this carbon, if it were to form the carbocation, would be much more stable and favorable to the formation of a secondary carbocation. And additionally, what we can see, or if we keep in mind, that this is a skeletal structure, and so, or skeletal diagram, so we know that we have a hydrogen there, and so we are able to undergo a hydride shift, and we would end up with an intermediate that has a tertiary carbocation despite this carbon not being involved in the double bond. And so we would then end up with our hydroxyl group attacking that carbocation, which is why we get this product. So as we can see clearly in the mechanism that we just walked through, carbocation rearrangements can occur. So if it is important to you that you're forming only the Markovnikov product without any sort of carbocation rearrangements being possible, then acid-catalyzed hydration is not going to be the reaction that you should be choosing, right? The second reaction, one that does not allow for any carbocation rearrangements, which you can again see the reason why by checking out my video on oxymercuration. Kind of spoiled it there, right? The second reaction is oxymercuration. Anyway, as I was saying, you can go and check that video out if you want to go and see a detailed explanation as to why oxymercuration does not allow for carbocation rearrangements, which becomes clear when we look at the mechanism in detail. But in this video, we won't be going, into the mechanism. But what we will be looking at is, once again, if we were starting off with the same initial reactant here, this alkene, and in this problem, or in this case, we are reacting it with the necessary rearrangement. The necessary reagents to undergo oxymercuration, we can see the product that we would form. So the reagents that you need to know, right? It's very important that you are aware of what reagents you're using and you're using them correctly, right? So we will be using HgOAc2 in water, followed by sodium borohydride. So these are going to be the two, or I guess somewhat, three reagents that we will be using for oxymercuration. So it's important that when you're setting it up, that your arrow, right, the reaction arrow here resembles something like this, where you have the correct reagents. But anyway, the actual products that we would form when undergoing oxymercuration would look like this. So you're forming directly the Markovnikov product without any carbocation rearrangements. Despite there being the possibility for the formation of a tertiary carbocation, if you look at the mechanism, we'll see that that would not occur if we are doing oxymercuration, and so we would end up with the secondary carbon having the hydroxyl group. So if that's what you were looking to do, then you should be sure to choose oxymercuration. And now that brings us to the third reaction, and this is one that we again have not gone over in previous videos, but it's going to be hydroboration. So for the hydroboration reaction, if we are looking at once again the same initial alkene, in this case there are a lot more reagents that you need to memorize, but again, so be sure that you do memorize these reagents. So on top, you're going to be first reacting with our BH3, THF, tetrahydrofluorine, and on bottom, you're going to have NaOH, H2O2, that's hydrogen peroxide, and H2O. Now, the order of these reagents does not matter, but just know that you have to have your BH3 and THF on top, followed by NaOH, H2O2, and H2O in any order of your choosing on the bottom. So what we'll see then as the actual product that we form for hydroboration is going to be, interestingly enough, just your anti-Markovnikov product. The anti-Markovnikov product. So if you can remember back to Markovnikov and anti-Markovnikov, we know that the Markovnikov product is the one that forms directly from the more stable intermediate. All right, so the anti-Markovnikov product is going to be the one that forms from the less stable intermediate. So in this case, that means that our hydroxyl is actually going to be attached to the primary carbon. This is something that we haven't really seen before, right? Whenever we talk about any of these reactions, we talk about how they proceed by Markovnikov addition, right? Where we have the hydroxyl or whatever group it is attaching to the carbocation, which is more or the carbocation intermediate, which is more stable. And in this case, we can see we're able to form a secondary carbocation, and even in some cases, if we have a carbocation rearrangement, we could even form a tertiary carbocation. But in the case of hydroboration, we are actually going to be forming a product that is forming from the intermediate involving the primary carbocation. So it's very important that you keep that in mind. So if you want to form a product where you are ensuring the formation of just that anti-Markovnikov product, you're going to want to choose your hydroboration reaction. All right, so those are those three reactions that you're going to need to know. Once again, it's going to be your acid-catalyzed hydration. You're going to be, excuse me. So it's going to be your acid-catalyzed hydration, your oxymercuration, and your hydroboration. So again, it's very important that you know the I guess the benefits or what it is that is different about each of these reactions. While they all involve the product at the end having a hydroxyl group being added, as we went through in this video, there are certain nuances and certain differences, right? So based on, especially again in the context of synthesis reactions or synthesis problems, based on what it is the product that you're trying to form, eventually keep in mind what reagents you're going to want to use, what reaction mechanisms you're going to want to utilize in order to get there. So that brings us to the end of this video. If you found it helpful, please show your support by liking and subscribing. Leave in the comments any questions you may have and suggestions for future videos, and I'll see you in the next one.